I'm happy to introduce Janet George. At Western Digital, she is building global core competencies in shaping, driving, and implementing big data platforms, products, and technologies. She previously served as the managing director, chief scientist, and big data expert at Accenture, where she was responsible for big data platforms, machine learning, and cognitive computer and open innovation. She also served as the head of Yahoo Labs and research engineering. She was inventing next-generation platforms, cloud infrastructure, and machine learning for big data. She's also worked at eBay and Apple. She holds a bachelor's and advanced master's degree with a distinction in computer science and mathematics with a thesis focus on artificial intelligence. Thank you for joining us.
Thank you very much. Good morning, everybody. My talk today is going to be about the anatomy of device physics and the world of device physics. I actually don't come from the device physics background. I kind of grew up in the advertising world, and I grew up with a search background, so that's pretty much my background. But the world of device physics is very exciting, and the data in that field, in that space, is huge learning for me. All my experience has been very practical, hands-on, on the field, so I'm very applied in my learnings. Okay, so what I want to cover today is just give you a background of what we're thinking about when we talk about data, why data is so important, what are the issues around data leading to device physics data, specifics about device physics data, what kind of complexity is associated with that data, what kind of things we try to get out of that data, how do we find the value in very high, large-scale manufacturing data, and then how do we apply machine learning and deep learning at scale to this data, the kind of data intimacy we need, and then finally leaving you with how we have embraced complexity and very large-scale leading-edge data. So this is a very famous slide. Everybody knows about the 3 V's that Gartner has been talking about for big data for a very long time, since 2012. And we're very familiar with volume, velocity, veracity, and so on, variety, and so on. Variety is still an issue, because trying to figure out structured, unstructured, semi-structured images, graph, bringing all this together, having all these different data talk to each other, we're still evolving. We've not gotten very good at trying to figure out how to make all the different types and kinds of data talk to each other. IBM very shortly started talking about veracity of data, and my focus is going to be around this veracity component of data, which I feel is the most misunderstood component of big data, or where the complexity really lies of big data. So when you think about veracity, it's the uncertain component of data. So to give you an example, in Yahoo, one of my jobs was really just to figure out, do machine learning on spam, on how attack was happening. And this was usually during registration. So when somebody registered in Yahoo, we couldn't tell whether the person registering was real or was a spam. And we were doing all kinds of machine learning, trying to figure out at the time of registration how they were entering their details into the registration form and whether they were real or not real. And it was very difficult, because as we were training machine learning to understand the characteristics of a normal behavior, we were also watching how the attackers were coming in and building out all these accounts. The data was very uncertain, and we were trying to deal with attackers. And we finally figured out, I think it was at 2 a.m. one night, as I was sitting with my team and trying to brainstorm on what are the specific characteristics of a spammer or an attacker, we found that they were cutting out the capture images and sending it to porn sites and having the porn field solve the capture near real time, humans. So there was no different way for us to figure out whether humans were solving the capture or whether some other human farm was solving the capture. And the key insight was the time that we captured for a regular human sitting at their desk to solve the capture versus it being captured and shipped to a server farm where a real human in some server farm was actually solving the capture and shipping that solved capture back to the site. So that's what uncertain data is all about, just to give you an idea. In the world of device physics, we're dealing with this fourth dimension of data. And again, I call this veracity of data. I call this uncertain data, uncertainty at scale. And when you're dealing with uncertainty at scale, so the device physics world, they create about 3 to 4 million wafers. It's very, very large scale. We have a lot of data. And with that data, and it's highly variable data, how do we understand that variability when the data is constantly changing, and how do we bring out insights from that data? So there's a couple of things that the device physics world do. One, experimentation. Their constant cost per bit is falling, and as you see cost per bit is falling, Apple is creating new and new phones, and all of the bits that go into this are at very low cost. And so as cost per bit falls, we have to do experimentation at scale. We have to move from technology nodes. So for example, if we started with a 21 nanometer, we go very quickly to 17 nanometer or 19 nanometer, 17 nanometer, and then finally at 15 nanometer. When we reach 15 nanometer, there's no more room to compress because there's only 13 electrons. So we can't do two-dimensional NAND. We have to start moving towards three-dimensional NAND. And three-dimensional NAND is something we've never done before. So now we're talking about multi-structures, multi-layers. So we have to do these technology node experimentations at scale. And when we finish the experimentation with the different technology nodes, we move into production at scale. And if we mess up at the experimentation stage, majority of production gets messed up, or a lot of cost in production, right? Because we can't afford to make any errors at scale in manufacturing. We have massive fabrication units in Japan. We work with our partner Toshiba, and we produce these wafers. So this data, what I found coming from the advertising world, is really leading edge data. We've never actually figured out how to tackle data coming out from Internet of Things, Internet of Machines, at scale, at us, in very, very variable form, extremely complex. So that's some of what I'm going to talk about. I call this heteroscedastic data. There's statistics we study about this: high variability, high change, how to model heteroscedastic data, what we can find from this data, how do we deal with all the variances, differences in samples, differences in errors, differences in what I call the cooking process, as wafers are cooked to be what they want as to be the final substrate or the final technology node. So I started to study the complexity of this data. And I found that it's very interesting when you start to just study the complexity of data. I found that this data, the wafer data, falls in the complexity factor of around quadratic. So it's more leaning towards this upper end of complexity, which I call quadratic exponential area. And so one of my jobs is really try to figure out how to tame this complexity and yet do machine learning at scale so we can find value, and we can find value that will reduce cost by not in the tens of millions of dollars, but in the hundreds of millions of dollars. That's a very big challenge because it's very applied, it's very practical. All the leaders that I've talked to in the manufacturing phase are very risk averse. And they're risk averse for a reason, because it's high production, high volume. And they want to be able to manage their risk. So they just don't want a model showing them insights. They want a model that can actually show very, very structural signals that can be actionable. So what are some of the challenges in the manufacturing data and the technology node creation? First of all, materials. We experiment with a lot of different materials. And materials, this is the physics part of it. Materials have a lot of issues. They have deformation, they don't bond, there's material buildup. Then we get into substrate. Substrate can overheat. There's actually a heat sink. We have to deal with resistive loss, deposition issues as we try to deposit different materials on top, trying to create the silicon. We're very aware of the thickness. The thickness has to be of a certain size. Warpage, as we try to put all these things together, the wafer itself will warp, and the way it warps is very painful. We have wetting layers. Oxidation is a big issue for us. If the wafer is waiting outside the equipment for long periods of time, it oxidates. Oxidation at scale is lots of dollars wasted. And finally, we have diffusion barrier, and the whole function of the wafer depends on DPPM, defects per parts per million. And we need to model out and capture all the known and unknown DPPMs, which is a very complex error recovery mechanism. In addition, we have coupling effects. So neighboring wafers, neighboring dies will cause behavior changes in others and adjacent track interferences. These are all the problems that we have to deal with in the manufacturing industry and try to get machine learning in the middle of this to try to figure out how to get value. And so when we start building machine learning models, it requires constant optimization because the data is highly variable. And we are training and retraining with change. So initially, it's a lot of just going in circles, taking the data, training, retraining, and so on and so forth. And then we can use very traditional mechanisms like ranking and weighting for figuring out the correlations for the DPPM. And one of the things I've learned is really getting intimate with the data, and I'll talk about that. I'm a big believer in allowing the topology of the data to dictate the machine learning techniques you're actually going to use on the data. Traditionally, machine learning people like to make some assumptions and use the assumptions on the data, linear regression versus random forest or naive Bayes or whatnot. And we found that when we use multiple modeling methods and we bring all that together, the data tells us which model actually suits better versus enforcing one model on the data. And also sometimes with linear regression, we have ability to fine-tune very nicely as compared to random forest or other methods. So 2 metrics we keep track of very closely in the device physics world. One is yield. We live and die by yield. Yield is performance. And the goal is to get very high yielding wafers. The companies our customers, for example, all the OEMs, Apples and Googles and Amazons of the world, they are very picky about yield. They want to see very high yielding wafers. They want to see top, we call them prime. They want to see prime wafers. Endurance is counter to yield. So if you have high performance, you don't have high endurance. And endurance is about lifetime value. Endurance is about data retention. We take the same piece of wafer, and as we are trying to get very high performance out of the wafer, we're also trying to get very high endurance, and the two don't work well together. So usually you'll see the graphs kind of like this, going in the opposite direction. And we've learned over time to figure out what the balance looks like between yield and endurance. And we cater to customers that have high yield needs and customers that have high endurance needs. And as we balance both of them, we try to make sure that we don't lose any single dies in the process. Because the wafer manufacturing industry is so cost intensive, we try not to lose anything. We actually even use the scraps. And we put it into small reusable chips. And so when we talk about yield, now we're getting into a different set of problems. One great news about the wafer itself is, as you can see, everything on the wafer can be imaged, it's a pattern, and we can look at all these patterns at scale. So this is where deep learning plays a very crucial role. We can train with these different patterns of failures and different patterns of success, green versus red. We can monitor at a die level. There's a lot of variability. So you can, I'm also starting to learn you can't have small sample sets. You have to have very, very large sample sets to see systemic issues of failures and things like that. So monitoring yield, managing yield, not just looking at failures, but looking at the clusters of failures, patterns of failures, edge versus radial versus center short versus side edges versus coupling failures. There's 300 different clusters of failures. And then within that failures, trying to look for what occurs the most, how is the highest impact, can the die still be used, not used, so on and so forth. So it's layered complexity. But the goal really is to get to 99.9% yield. And this is like a dream. With our highest running technology node right now, 1Z, which is going to be running till 2018, and we're building the next one that comes after that, which is a 3-dimensional NAND, we are looking at 92% accuracy on the yield, which is very high from industry standards. Only by leading storage providers have been able to accomplish that. So endurance. When we talk about endurance, different deal. Right now we're talking about retention of data. We're talking about lifetime. And this is constant cycling of the chip and trying to figure out how the data is retained at different cycles. So we start with 10,000 cycles, 5,000 cycles, 2,000 cycles, 1,000 cycle, and customer comes back and says, can you show us at 5.5? Right? And so we can't test for every single cycle because it's very, very expensive to test. So we can do like benchmark tests, and they're not enough because we have to be able to predict what the wafer or the die will do at different test cycles that is not actually tested for, that are ad hoc requests from customers or OEMs that come back to us. So predicting retention cycles have been wonderful for us because we've used machine learning at scale here, and we've had a great deal of holy grail type awakening moments looking at how we were able to predict the right amount of retention given the right amount of yield. Failure classification. I like this a lot, and the reason I like the failure classification and clustering area is because used to be we had these prime dies, and then I call it like prime shirts or prime dies, and then we have this intermediate set of dies that are not so prime, somewhat in the middle, and then we have these loser cases, which are basically dies that just don't function at all. They don't even start. So what do you do with that? And we had different business streams based on these. And we took all the low-end dies and we used to mix them with other dies and then sell them. And now with the classification, we found a more fine-grained tailed failures for these dies. And so now we are able to create entire businesses from going from high-end to mid-range to the third category. So we are able to create a whole spectrum of new revenue that we can generate looking at the different kind and type of failures and the impact of those failures. So we are able to mix and match different failures. The one that doesn't start at all, we can mix that die with the one that somewhat starts, right? And then with another die that starts but doesn't do anything else. So combining all these different things, we are able to put different pricing, different packaging on the project and actually sell them. So this is an area of machine learning that's actually revenue driven, brings back revenue to the company directly, given how much work is being done here. And we are able to do very complex error recovery, which is fascinating, getting into the tail part of the error. Okay. So this slide I put together just to show you what I was dealing with when I first came in here. I basically put together data in different big buckets, just for my own sake to try to simplify it. So manufacturing data, we talked a little bit about that, the prep, the measure, the clean, all that, testing and screening. And the holy grail is really finding Nemo, right? Finding all the correlations, values, permutation, combination. Can I actually find a path, a structured signal, not a one-off correlations, but more what I call structural correlation, or a correlation, if I have like 35 response variables and each variables have 500 dependencies on correlations, what actually matters? And is there a discovery of a new correlation? Can I build a machine learning correlation engine that can show me every permutation combination of these correlations that human domain experts cannot even foresee of getting there? But when we see a new technology node, that's a three-dimensional technology node, and we understand the failure at experimentation coming from a correlation that was dynamically recovered from the field, very powerful. So I'm about 3 minutes, I guess. Let me quickly talk about this very simple example because I want to bring home the point about data. So as I was doing all this complex stuff, HR came to me and said, hey, can you just do something simple for us? Just predict employee performance. This is as simple as it can be. It's not a complex problem. Can you tackle this, right? And I said, okay, let's try that. That's very simple. Where's the data? What do we have? And what do we need? So they said, okay, let's get into the analysis. So we quickly got into the analysis, variable importance, predictive value. We have our own employees. We have our own managers. They're all calibrating our employees, and we have data. So we went in and we looked at all the performance variables. And this example is a little representative because it actually shows you, after we did a lot of work with the data around demographic, job, compensation, performance, none of that data actually mattered to do predictive, to predict an employee's performance. What mattered was how they worked in a team together, and what did the calibration data actually look like, and were they high potential employees, and were they in a high potential program, things like that. And very quickly, we weighted the importance of the variables, ran a different kind of models, came up with the results. And then I looked at them, and they looked at me and said, what's the key findings? And we said, well, what the manager calibrated is what the machine learning model came up with. So they said, well, what did we learn? Well, nothing. Because we took the calibration data that the managers had, fed it to these models, and the models spitted out what the calibration model said. So inherently, our data was very biased, right? And so we have to start a discussion around how do we change the game with data? What data should we be collecting? We shouldn't take data that's sitting in an existing company, in an existing database that's been around for a very long time, that's fitted for certain tools, and throw it at machine learning and say, can machine learning show me something different, right? Can machine learning beat a domain expert? And the answer is no. We have really got to try to collect unbiased data. We have to get away from bias. We have to look at raw data, create annotations and lineage at scale, unfitted for existing tools, because when we do that traditional ETL, there's a lot of loss of data. And that was one of my key findings. We ETL'd our way into every yield tool. And we already knew what the tool was going to give us. And then I had to take the same data that the yield tool was reporting out and say, Janet, can you discover something in machine learning that we don't already know? By the way, we have 3 PhDs, and we are device physics experts, and we have material science physics people over here, and you, the machine learning person, tell us something we don't know. So I was on this chase, trying to tell them something they didn't know, and I was getting nowhere, because inherently the data didn't exist. And so we have to overcome this thing about data loss and trying to figure out how do we capture data. So now we've gotten to the place where this data is coming out of the Internet of Things. We capture the data from the Internet of Things in its raw form. And so I want to leave you with this. Developing an intimacy with data is really crucial, and with the domain experts. Asking the right questions, critical thinking, observing the signals, and really just looking at systemic patterns. That's how my data looks in the tool, and it's fitted for the tool. But if I actually look closely and I change the data, or I collect different data, I can actually get a completely different result from similar data, but with more around it, without the data loss, right? So we're looking at data is so tricky. The way we look at the data and the way we play with the data, we can see many different things about the data as we ask the right critical questions and so on. So that's pretty much my last slide. Key takeaway is the leading edge of data coming from the Internet of Things, machine data, is heteroscedastic data, very highly variable data. Learning to do machine learning on this kind of data is our new challenge. And this is where the leading edge of work remains to be done. Thank you.